Hi everyone, here is another presentation of indeterminate limits. You can use this video as a follow-up to the video that you have looked concerning L'Hopital's rule, and more specifically in this video, we're going to examine other types of limits than those that were already discussed. We have seen how to treat 0 over 0 forms and infinity over infinity forms using L'Hopital's rule. In this case, we're going to use forms for which strategies are necessary in order to be able to apply L'Hopital's rule. 0 times infinity, or 0 times minus infinity, are considered indeterminate forms of limits. We encounter 0 times plus or minus infinity forms in cases where we have a limit where the product of two functions f and g go to 0 in one case and to infinity in the other. The strategy that we will use in order to solve these limits will be to reverse either f of x or g of x to create a fraction. So in other words, we're going to rewrite the limit as x goes towards a of the product f times g either as the limit as x goes towards a of f divided by 1 over g, or the limit as x goes towards a of g divided by 1 over f. And from this point, L'Hopital's rule will be applicable most likely than not. For instance, here we have the limit as x approaches 0 from the right of x times ln of x. This is actually a 0 times minus infinity form, remembering that ln of x is a function that has a vertical asymptote as we approach 0 from the right. So the strategy we're going to apply here is to flip either x or ln of x, and it would seem like the simpler solution here to take x and to rewrite it as 1 over x. You'll agree that flipping x at the numerator into 1 over x at the denominator leaves the two expressions equal. It's just the format that is different. Now at the numerator, ln near 0 goes towards minus infinity, and at the bottom, 1 over 0 plus goes towards infinity. So this is a minus infinity over infinity form, so one for which we can use L'Hopital's rule and replace ln of x by its derivative as well as 1 over x by its derivative. The derivative of ln of x is 1 over x, and that of 1 over x is minus 1 over x squared, where we treated 1 over x as x to the minus 1. Before we go any further, we have two fractions that can be simplified by replacing the division by a multiplication by the reciprocal, and then we can simplify the common x's, and by direct substitution, the limit result we get is then 0. In the second example, we have an infinity times 0 form, because as x goes to infinity, obviously x is going to become infinite, but then again, e to the minus infinity heads towards 0. So again, a choice has to be made about who we will flip. Either we bring x to the bottom as 1 over x, or we flip e to the minus x to the bottom, which is actually the simpler case here because 1 over e to the minus x is simply e to the x. These are laws of exponents that we're using, and in fact, we could have gone from the first to the third step directly. Now, direct substitution will tell you that this is an infinity over infinity form, and therefore L'Hopital's rule allows you to replace x and e to the x by their respective derivatives. On the numerator, the derivative of x is 1. On the denominator, the derivative of e to the x remains e to the x, and direct substitution will give you a 1 over infinity form, which goes to 0. All of this would not have been possible if, first and foremost, we had not flipped one of the two expressions, and secondly, if we had not applied L'Hopital's rule. Here's another example that involves x and an exponential function, but where the choice we will make is slightly different. As x goes towards 0, obviously we have x as a multiplier going towards 0, but 1 over x would then be heading towards infinity, and e to the infinity goes to infinity. So if we apply our limits appropriately, we'll recognize this is a 0 times infinity form. We have the choice, once again, to flip x to the bottom as 1 over x, or to flip e to the 1 over x to the bottom as e to the minus 1 over x. And the choice we'll make this time is to flip x into 1 over x at the denominator. Perhaps you can already guess why this will be a useful operation. Do you notice how the numerator and denominator have a 1 over x in common now? Not that they can be cancelled directly, but we'll see that cancellations will take place along the way. Currently, 1 over 0 plus is a plus infinity form, and at the numerator, e to the plus infinity will go to infinity. So this is an infinity over infinity form. L'Hopital's rule allows you to replace top and bottom by their respective derivatives, and this is where we're going to see cancellations take place. The derivative of e to the 1 over x is e to the 1 over x times 1 over x prime. This is the chain rule we're applying. In fact, I'm going to be lazy, and I won't even bother calculating 1 over x prime, because 1 over x differentiated is also what's happening at the denominator. So those common derivatives can simply be cancelled. 1 over 0 plus is heading towards infinity, and e to the infinity becomes really big. So this limit diverges to infinity. There are 3 different limit forms that are indeterminate and will require a little bit more than just L'Hopital's rule or flipping terms. 0 to the 0, infinity to the 0, and 1 to the infinity are forms that are considered indeterminate. In other words, they do not reveal an answer, and more work has to be done. All of these forms are usually observed when a limit is applied to a functional base and that has itself a functional exponent. So f of x to the power g of x. And either of these forms are obtained, 0 to the 0, infinity to the 0, or 1 to the infinity as x approaches a. So here's the strategy we're going to use this time. We're going to give a label. I would usually use letter L, but it doesn't matter the name we choose, that is equal to the limit that we are initially solving. So L is equal to the limit as x goes to a of f of x to the power g of x. And we will then apply a logarithm to both sides. So ln of L equals ln of the limit of f to the power g as x goes towards a. A property of limits considers legal to bring in logarithms within the limits because of their continuous nature. And for the most part, many of you will simply head to this step directly, which is fine. So the reason why incorporating a logarithmic function is useful is that now g of x, the exponent of f, can be converted into a coefficient. It's again a property of logarithms here, which moves the exponent to the front as a multiplier. And typically this limit form will have now become 0 times infinity or infinity times 0. So we'll fall back onto situations that we have discussed a little bit earlier in this video. So 0 times infinity mean we're either going to flip g of x or ln of f of x. We're going to have to see depending on a case-by-case basis. Possible scenarios. So if the ln of the limit is finite, so in other words, if you get a number from the answer to ln of L, then the original limit will simply be equal to e to the ln of L. If the ln of the limit you have solved is infinite, it means the original limit itself was infinite. And if the limit that you have solved gives you minus infinity, it means that the original limit itself was 0. For example, here we have a limit as x goes to infinity of 1 minus 2 over x to the power x. Always start by doing direct substitution. In this case, you'll notice a 1 to the power infinity form is obtained. So this is a situation where we can simply not just factor or flip a term. So instead, we're going to use the strategy that we discussed earlier. So we're going to give this limit a name. I'm going to call it L. L stands for the limit as x goes to infinity, 1 minus 2 over x to the x. We'll incorporate a logarithm on both sides. ln of L equals the limit as x goes to infinity of ln of 1 minus 2 over x to the x. Properties of logarithms allow me to convert x, which used to be an exponent, into a multiplier in front of ln. Here's where we have to visualize or reevaluate to see what kind of form we have. As x goes to infinity, so the coefficient is becoming infinite, in the parentheses, 2 over x is becoming 0, and that leaves ln of 1, which is going to 0. So this is in fact a 0, an infinity times 0 form. And infinity times 0 forms are solved by making a choice, by flipping one of the terms, and definitely the simpler of the two here would be to flip x as 1 over x, which I've done already. For those of you who are replacing or doing direct substitution at every step, you'll notice this is now a 0 over 0 form, which finally allows us to use L'Hopital's rule. So L'Hopital's rule on an expression of form ln of u is 1 over u times u prime. So 1 over 1 minus 2 over x times 1 minus 2 over x prime over u times u prime. At the bottom, 1 over x is differentiated also because of the application of L'Hopital's rule. When we calculate the leftover derivatives, 2 over x squared at the numerator minus 1 over x squared at the denominator, you'll notice that there are x squares there that can be cancelled. We can simplify the expression. And in the end, minus 2 over 1 minus 2 over x is all that is left. Applying the limit, 2 over infinity goes to 0, and minus 2 is all that is left. Now, very important is to recognize this answer is the answer not to the original limit, but to the ln of the limit. To isolate L, we would apply an exponential function on both sides, and therefore the original limit is e to the minus 2. Therefore, the original limit that we solved has a determinate answer, e to the minus 2, or 1 over e squared. The same steps can be applied to x to the root of x, which is a 0 over 0 form. We would label this limit as L, apply a logarithm to both sides, use the properties of logarithms which allow to convert root of x as a multiplier instead of an exponent. Then a choice can be made to flip one of the terms, and of the two, the simpler case is 1 over root of x. This is now an infinity over infinity form. It's actually a minus infinity over infinity form. L'Hopital's rule can be applied to top and bottom, and before things get out of hand, these fractional terms can be simplified by flipping the fractional denominator, and reevaluating the limit will give 0. I'll expect you to retry these steps and convince yourselves that they're right. Since the ln of the limit is 0, then the original limit is 1. In other words, the original limit is 1.